One thing we noted earlier was that not all systems have a unique solution. Some are dependent and some are inconsistent. So how do you recognize those when you're solving the system? So let's take a look at this example. We'll solve this one by substitution. We'll take the first equation and we're going to solve it for x. So if we do that, we're going to find out that x is equal to 2 minus 3y. We're going to replace that into the other equation. So we'll have 3 times, we're replacing x with 2 minus 3y plus 9y is equal to 6. So we have 6 minus 9y plus 9y is equal to 6. In other words, we now are left with a statement that says 6 is equal to 6. So that's very unusual. We have no more variables left, and we have a true statement that 6 is equal to 6. So what does this mean? So we have no variables, but we have a true equation. This is a sign that we're looking at a dependent system. Remember, that means that both of these equations, were you to graph them, would be exactly the same line. In other words, there's an infinite number of solutions. Any ordered pair that makes the first equation true will automatically make the second equation true. Let's take a look at this next example. Notice that this next example, x is already solved for in the first equation, so we just have to take this value and substitute it into the other equation. So if we do that, we'll replace x with 9 minus 2y. So we have x, 9 minus 2y, plus 2y is equal to 13. And notice that if we solve this, we're looking at this statement, 9 is equal to 13. So now we have no variables left, but unlike the first one, we're looking at a false statement. It is not true that 9 is equal to 13. So what does this mean? This means we're looking at an inconsistent system, and that there is no solution. There's no ordered pair. There's no x and y that would make both of those equations true simultaneously. If you were to graph these lines, they'd be parallel. So here's one for you to try. You solved a system of equations and ended up with this statement. What does that mean? Okay, so let's look at our last method for solving a system of equations, and that's by the method of addition, or sometimes called elimination. So in this method, you line up one of the variables, either x or y, so that it has the same coefficient but with opposite signs, and you may need to multiply to do this. You add the equations together. This will eliminate one of the variables. That's why this technique is sometimes called addition, sometimes called elimination. It leaves you with an equation that you can solve, and then finally you solve for the remaining variable. So let's take a look at this example. What I'm going to do is I'm going to line up the y's. Now notice that the first equation has a coefficient of -7, so I'd like the bottom equation to have a coefficient of +7. So I'm going to multiply both sides of that equation by 7. So now the system will look like this. 2x minus 7y is equal to 2, and 21x plus 7y is equal to -140. And now we're going to add the equations together. 23x, 7y and -7y are 0. In other words, y has been eliminated, is equal to -138. And if we divide both sides by 23, 138 divided by 23 is 6. So x turns out to be 6. So now we know that the x-coordinate of the point of intersection is 6. We have to find the y-coordinate. In any of these equations, it doesn't matter which one, you can replace x with 6 and solve for y. So I'm just going to use this first equation, and I'm going to replace x with 6. That tells me that 2 times 6, in other words 12, minus 7y is equal to 2. Subtracting 12 from each side, we have -7y is equal to negative 10. And dividing both sides by 7, we have y is equal to 10/7. So there's our solution to that system. Okay. Oops, I thought that was a little weird. Let me go back and try that again. I think I just miscopied this equation. So that equation isn't, oh yeah, it is. So 2 times 6, 12. 12 minus 7y is equal to 2. I'm just double checking because it would have been so nice if it had come out to be 14 with a solution of 2. But I don't see any sign mistakes, so I really do think that one came out with a fraction. Here, let's try another. Now notice in this system, here's an example of a system where you sure wouldn't want to use substitution to solve it because none of those variables look friendly to solve for. All of them will involve dividing and possibly introducing fractions to your work. So here's an example of a system that really is made for solving with elimination or addition. Notice you can line up the x's or the y's, it doesn't matter. If you line up the x's, you might be choosing to make a 10 and a negative 10. If you're lining up the y's, you'll probably be getting a 30 and a negative 30. So I'm going to, let's see, I think I'll line up the y's. So I'm going to go for 30. So on the bottom, I'm going to multiply it by 3, giving a negative 30. And then top, I'm going to multiply by negative 10, or excuse me, by 10, giving a positive 30. All right, so let's see what we have now. 20x plus 30y is equal to negative 160. 15x minus 30y is equal to 90. Adding these together, 35x, y has been eliminated, is equal to negative 70. And if we divide both sides by 35, we'll find out that x is equal to negative 2. And now that we know what x is equal to, we can substitute it in anywhere to solve for y. So I'm going to take this first equation here, and I'm going to substitute negative 2 in for x. 2 times negative 2, that's going to give us negative 4 plus 3y is equal to negative 16. And then these are easy equations to solve. So we have 3y is equal to negative 12. Dividing both sides by 3, y is equal to negative 4. And so the solution to this system is the point negative 2 comma negative 4. And now here's one for you to try. So go ahead and pick a variable to line up. If you're lining up the x's, you'll want 14 and negative 14. If you're lining up the y's, you'll want, let's say 10 and negative 10.